Okay, let's continue our discussion of angular motion with homework set 31. This homework set picks up pretty much where the last one left off with problem 3, using these kinematic equations for rotational motion. The 4 equations that are similar to those linear equations on page 23 of your textbook. Now, problem 7 involves a stationary bicycle. I don't know how to draw one of those, but it's got a C, it's got handlebars, and it's got some stand down here. Anyway, we're told that the radius of the wheel is 0.5 meters, and we're told that this the stationary bike originally is not turning. Now remember, we solve these problems by making our list of variables, our angular displacement, angular acceleration, angular velocity, and time, always those 5 variables. And we have to find 3 of these from the problem statement. Well, we're told that this bicycle wheel initially is not turning, and that it has an angular acceleration of 2.5 radians per second every second. We're also told that we're looking for a time, during a time, in which we go 20 revolutions with the wheel. And we're asked how long did that take? That's part A. So in part A, we have these 3 pieces of information. We want time, so that makes this our who cares. And just like in that problem 3 in the last homework, we're going to use this 3rd equation that doesn't have omega final in it. And just like in that last problem, we have to convert revolutions into radians. And since we have 2 pi radians for each 1 revolution, this was going to be 40 pi radians. So I can put in 40 pi radians. There's no initial angular velocity, so this is equal to 1/2 times 2.5 radians per second times delta t squared. If I solve that for delta t, lo and behold, the numbers are cooked again, so that we once again get for 10 seconds. Now B asks us to find the final omega for the wheel. So now I know that delta t is 10 seconds, and now I want omega final. Now I could solve this the same way that I did problem 3. I could just say that this is going to be omega initial plus alpha delta t. But just for kicks and giggles, let's just try a different approach. There's 3 different equations over there that are going to give me the same right answer. So let me use the 4th equation. So again, this is 0, and what I get is omega final squared is equal to 2 times 2.5 radians per second squared times 40 pi radians. And if I solve that for omega final, I get 25 radians per second. Okay. So we have the last part here, a part C, And that part C asks us, well, what if this stationary bicycle was not so stationary? What if, it's one of those newfangled bikes where you put on the headset and you actually feel like you're going down the road? If this thing could actually move, how fast would you be going down the road? In other words, what would your linear speed be? How fast would trees be coming towards you if you were up to this angular speed? Now, you remember from class that we had a rolling condition, or it should be called a rolling without slipping condition. And that rolling condition was that the linear speed of the bike is related to the angular speed of the wheel, and the fudge factor that you have to multiply it by is going to be the radius of the wheel. Now, because of these relationships here and the relationship between the linear variables, I can write two more equations, and that is that how far you get down the road with your bike is going to be related to how far the wheel rotates, again with the fudge factor being the radius of the wheel, and the linear acceleration of the bike is going to be related to the angular acceleration of the wheel, again the fudge factor being the radius of the wheel. Now in this case we're asked to find the linear velocity of the bike, and so for part C we just say the linear velocity of the bike would be the radius of the wheel, which is given as 0.5 meters, times the final, we found this to be 25 radians per second, and so that's going to be 25 radians per second, and that's going to be half of 25 or 12.5 meters per second. Well, what happened to the radian there? Well, you remember that the angle defined in radians is just the arc length divided by the radius. Well, the arc length is measured in meters and the radius is measured in meters, so the radian doesn't have any actual units. It's a placeholder to remind me that I'm talking about rotational motion, but I can make it disappear anytime it's inconvenient. And right now it's inconvenient because I measure velocity, linear velocity, in how many meters I get down the road each second. Okay? So that's problem 7. Let's look at problem 8. Whoops, erased a little more than I wanted to over there. We're going to need those equations. Fix it. Okay, we don't need that arrow. This next problem 8, we're told that a truck is accelerating uniformly from rest, and after 5 seconds, the 50 centimeter radius wheels on the truck have an angular velocity of 30 radians per second. So let's again make our list of the variables. And again, this thing is starting from rest, so the initial angular velocity of the wheel is 0. We're told that the final angular velocity is 30 radians per second. And we're also told that it accelerates for 5 seconds. We also know that the wheel has a radius once more of 1/2 meter or 50 centimeters. So part A of this asks us to find the magnitude of the angular acceleration. That makes the angular displacement the who cares. So I come over here and look for a formula that doesn't have angular displacement in it. Well, there's angular displacement, there's angular displacement, there's angular displacement. I want to use this first equation. So for A, I have omega final is equal to omega initial plus alpha delta t. This is going to be 30 radians per second is equal to, that's 0. So it's going to be alpha times 5 seconds. And that gives me an alpha of 30 divided by 5, or 6 radians per second squared. Now part B asks us, what is the final velocity of the truck? Linear velocity. So again, we just use the rolling condition. The truck has a linear velocity that's equal to the radius of the wheel times the omega of the wheel. So this is going to be 1/2 meter times 30 radians per second, and that's going to be 15 meters per second, or about 30 miles an hour. Now, the last part of this question asks us, through what total angle does each wheel turn during these 5 seconds? Well, now we're looking for this. We already found that this was 6 radians per second squared. And now, because we have 4 pieces of information, there are 3 equations that will all give me the same right answer. So I'm going to use that second equation. So that's going to be 1/2, this is 0, times 30 radians per second times 5 seconds. And so that is going to give me 75 radians. Okay, 15 times 5. Okay, that's problem 8. And I'm not going to pause here because you can hit the pause button. I'm going to leave those equations up there because we're going to need those for problem 10. Problem 10 has one of these rotor rooms where we've got Billy, and Billy's pinned up against the wall. Once it gets spinning fast enough, we drop out the floor. And so this room is spinning about an axis, okay? And we're told that it spins up from rest to a final angular speed, after which the floor drops out. The ride, which starts from rest, after 15 seconds of constant acceleration, the room has made a total of 6 revolutions, and the radius of the room is 2 meters. So this distance here is 2 meters. If we make our list of the variables, what we know is that it starts from rest and that it accelerates rather, for 15 seconds, and that during that time it goes through 6 revolutions, And if we multiply that by 2 pi radians for each revolution, we get 12 pi radians. Okay? Now the first part is asking us to find the angular acceleration. So this is our goal, to find alpha, and that makes omega final the who cares. So we use the equation that doesn't have omega final in it for part A. And this is 0, so that goes out. Whoops. So this is 12 pi radians is equal to 1/2 alpha times 15 seconds squared. And that gives me an alpha of 0.34 radians per second squared. Okay. In part B, we want to find the final angular speed of the room. So now this is promoted from who cares to this is what we're looking for. And this is 0.34 radians per second squared. Well, now I want to use an equation that has omega final in it. I'm going to use this equation here. And so for B, I've got delta theta is equal to 1/2 omega initial plus omega final delta t. And this is 12 pi radians. This goes out, and that's equal to 1/2 times that's what we're looking for, omega final times 15 seconds. And we get an omega final that is, if you will believe it, it works out to be 5 radians per second. Okay? Isn't that handy? Okay. Yes, indeed. Okay, now part C. Find the magnitude of Billy's centripetal acceleration after the 15 seconds. So we know that centripetal acceleration is equal to v tangential squared over r. In class, we found that we could also write this as omega squared r. And we're using the rolling condition there, the rolling without slipping condition. And so this is going to be 5 radians per second squared times 2 meters. And that's going to be 25 times 2, or 50 meters per second squared, or 5 times the gravitational acceleration. So essentially, Billy is pulling 5g as if he were an astronaut here. Now, the last part of this problem asks us to find the minimum coefficient of static friction such that that Billy's going to not slide down and get caught in the gears down there. Well, if I look at Billy up against this wall, a free body diagram for Billy is going to have a weight force, Earth on the Billy, and it's also going to have a normal force, and this is going to be the wall on the Billy, and it's going to have a friction force, and that's going to be a static friction force by the wall on the Billy. Now, I know that this diagram had better screen towards the center of the circle that Billy's going in. So this is going to have a centripetal acceleration equal to 50 meters per second squared that way. So if I look at this free body diagram, what that tells me is that there's no acceleration up or down. So this is going to be mg. And if there's no acceleration up or down, the static friction also has to be mg. Okay? Now I can find this net force by using F net equals ma. Well, if I call that the positive x direction, the only force in the x direction is going to be that normal force by the wall on Billy. And that's equal to the mass times A. This is centripetal acceleration. And instead of writing 50, I'm going to write it as 5 times g. Because 50 meters per second squared is 5 times 10 meters per second squared. So if I look at the equation for static friction, it has to be less than or equal to mu sub s times the normal force. Okay? If this is the friction by the wall on Billy, this will be the normal force by the wall on Billy. Well, if I divide both sides by n, I get the friction static wall on Billy divided by the normal force by the wall on Billy is less than or equal to mu sub s. Now the friction force we said was m times g. The normal force we said was 5m times g. So this is going to be 1/5 or 0.2. So let's see what this is saying. This is saying that the coefficient of static friction has to be bigger than or equal to 0.2. Now it can be anything bigger than 0.2. I mean, if you use, if you smear that wall with super glue, it's going to be a huge value, and he'll stay stuck to the wall. But they're asking us, what's the minimum? What's the smallest value? How slippery could this wall be and have Billy still pinned to the wall? And the answer is the smallest value of mu sub s would be 1/5 or 0.2. Okay, this has been homework set number 31. Hope you're all still on the bus, people.